something like 2 hours to do it. Okay, so this is what would happen. Most of you did very well, but this is going to be my just to just remind you some points that you missed. Okay, this is the first one. You know that anytime you have the power of the t, you have to use the derivative. So you have the t squared, so you need the second derivative. So we find the Laplace of the sine of the t, sine of the 3t, which is 3 over s squared plus 9, and you differentiate it twice. That give you Laplace of a t squared sine of the, sine of the 3t. The final answer is this one, unless you put them together. Negative 6 over s squared plus 9 plus 24s over s squared plus 9 cubed. Okay, some of you simplify, that's fine. But if you leave it, we accept it. That is going to be the first one. Okay. So the second question. Okay, so that was the first one, part 1. Okay, and the part 2, you have to change this function into the unit step function. As usual, you know that you pull out the cosine of t. The leftover is going to be the leftover is going to be 0, and the sine of the t minus pi third, you change it into the cosine t plus the unit step function at the base pi third. Everything is nicely created. So the Laplace would be the first one, s over s squared plus 1. The second one, it's e to the negative pi s over 3, 1 over s squared plus 1. Okay, the standard one, again, you can put them together. Even if you leave it as is, we accept it. So that's one. That's question number 1. Question number 2, you want to find the Laplace of t to the 5th, e to the negative 2t. You have 2 different methods to do this one. Okay, one way to do it, because of the e to the negative 2t, we can use the translation theorem. We find the Laplace of t to the 5th first, which is going to be 5 factorial s to the 6th. And then we change the s into the s plus 2, because e to the negative 2. So the final answer would be 120 over s plus 2 to the 6. Some of you write 5 factorial over s plus 2 over to 6. You're not done. It's such a short answer. So you have to take care of the 5 factorial. 120 over s plus 2 to the 6. That was the first part. Okay, the second part, that idea that we use several times. Okay, the function is t minus 3 u2t. Remember, we are going to use the translation theorem. So we need to have t minus 2. So we break it into t minus 2 u2t minus u2t, and then you find the Laplace transform. The standard formula, the final answer, e to the negative 2s over s squared minus e to the negative 2s over s. Okay, any question? Now, the bad one that you did is number 3. Some of you missed the algebra point, which is very bad. Make sure you're not going to repeat it. And this is it. The denominator is going to be quadratic one. Okay, you know that you have to make a complete square. You see, you get s minus 1 squared plus 1. In algebra, you can simplify the fraction by dividing by the common factor. S minus 1 is not a common factor. It's at end. Some of you cancel out s minus 1, and then you get a mess, and you couldn't continue. Okay, so s minus 1 over s minus 1 squared plus 1 is nice. You cannot simplify it. Okay, so that give you, you know that you are going to find the Laplace of s over s squared plus 1, and then translation of e to the t. So it's going to be e to the t cosine t. You change the t to the t minus 3, and the unit step function at 3. So the final answer is this one. u3t e to the negative t minus 3 cosine of the t minus 2. Okay, the next one is standard. Okay, you just break it. All of them are unit step function, u1, u2, and u5. That's number 3. Number 4. Number 4, I told you it's a misprint. No, it was not a misprint. There is a nice Laplace transform that you get involved. But I just feel that it would be unfair. So if you did everything except finding the Laplace inverse of 1 over s squared plus 1 all square, I give you your full grade. Okay? This, that you just find the Laplace transform of both sides, you put them together, and eventually you arrive at this format. Laplace of f of t is 1 over s squared plus 1 all squared, and the rest. Now, the rest, the Laplace inverse gives you sine t cosine t. Your difficulty is the first one. Laplace inverse of 1 over s squared plus 1 all squared. There is something we call it convolution, that we don't talk about it. If you know that one, you can do it. But it's fun to do it without that. So there are two of these type of format in the Laplace transform. This is one of them, 1 over s squared plus 1 all squared. The other one is s squared over s squared plus 1 all squared. It's like the experience of the power series. When you want to find the power series representation of a function, remember, we try to break it. We try to use the derivative. So the fun part about this one is this, okay? This can be the derivative of the, okay? It can be the derivative of the first or the second derivative of the sine t or cosine t. So what I did over here, you see, this is it. I created 2 on the top. So I changed the 2 into the 1 plus 1, s squared minus s squared plus s squared. If you break it into parts, you arrive at this one. 1 minus s squared over s squared plus 1 all squared, and the second part. The first part is the derivative of the Laplace of the cosine t, and the second one, you have the sine t. You have a transformation of, just a 1. So the Laplace inverse of 1 over s squared plus 1, if you believe it, it's going to be negative 1/2 t cosine t minus 1/2 sine t. Even if you want to use the convolution, it's complicated. And this method is much, much easier. So, if you see this, you may see it in application problems. Just think about differentiating the Laplace of the sine and the cosine. You are going to be around that one. Okay, but anyway, I'll give you the point. But I wanted to see the solution, really. It's a nice problem. It's something that we learn. Okay, that's number 4. Number 5 is straightforward. Most of you did right. Okay, again, you have the case that you have to make a completing the square. You have negative 3 over s squared minus 6x plus 13. A transformation, s goes to s3. Final answer, negative 3/2 e to the 3t sine of the 2t. You didn't have any difficulty for this one. Most of you did right. Okay, number 5. Number 6. You missed something here, right at the beginning. You have the equation on the other side, you have h of t. You have to find the Laplace of h of t. This is not the unit step function. Okay? You see? This h of t is not the unit step function. It's a kind of the complement. So it's a 1 minus, okay? It's a 1 minus u 3 pi t. So when you want to find the Laplace of this function, the Laplace would be 1 over s minus e to the negative 3 pi s over s. This is only one that you missed, some of you. Otherwise, it's a standard. You take the Laplace transform both sides, and eventually we get a nice function. So this is the final answer. Sine t plus 1 minus cosine t minus u 3 pi t, and the transformation of t goes to the t negative 3 pi. Okay, that's one. And number 7, good luck. This is, that was a heavy question, really. But I was very glad to see, most of you did it right. So it means we are very patient to get this one through. It's a linear system, but you know that this is not a linear. It's a kind of, you have those function e to the t negative t. It's algebra. You have to take the Laplace transform of both sides and patiently find the Laplace inverse of both sides. Okay, it's involved very much. I couldn't get time to rewrite it because it's going to be, a long solution. But I do it when I post this one for you. Okay, it's going to be involved. If you want to make it quick, as you did, some of you, you may use the sine hyperbolic function. Okay, sine hyperbola and the cosine hyperbola. That will help you to write this one. And believe it or not, this is a problem from your book. if you check section, I think it's section 8.2, this is problem number 2 in your book. Okay, so this type of system, it can happen. So that's why we want to check it, because you are a very good student. So, and you proved it because you were able to solve it. Number 8, that's an easy one. Okay, linear system. When it's a linear system, you know that you have to use those eigenvalues idea to solve it. Okay, some of you try to solve it, this one by the Laplace transform. Okay, it's a homogeneous system with a constant coefficient, so eigenvalue 1, the best way to do it. Okay, you find the eigenvalues, you know that it's going to be positive -1. Then you find those eigenvectors, you put them together. Final answer is C. You see that's the one, C111 e to the t. We are going to continue this tonight. C213 e to the -t, but since in the system expressed in terms of the x and the y, so the final answer must be expressed in terms of x of t and y of t. If the system given to you in matrix form, means x prime equal to the a times x, you leave the solution as a vector, as a matrix, okay? But if it's going to be in terms of the x and the y, you have to find the x and the y for us, okay? So the final answer is C1 e to the t plus C2 e to the -3, and the second part, C1 e to the t, 3 C2 e to the -2. That's number 8. Number 9, that extra question. Okay, you were supposed to answer 8, but most of you answered this one too. It's a system of the equation of a second order. Okay, second order. Again, nicely, most of you did it. You know that you find the Laplace transform, it takes a little bit more time to do it. But at the end, it's a nice problem. The final answer is going to be, okay. So there was a coefficient that I was not quite sure about it. Some of you got 3/2, but I got 1/2. But I think that 1/2 is correct. This is it. It's a -1/2 t minus 3 radical 2 over 4 sine of the radical 2t, and the -1/2 t plus 3 radical 2 4 sine of the radical 2t. Some of you got 3/2, but probably I gave you a point, but I think it's a -1/2 because I checked it. Okay, so that's it. It was a tough test, but most of you did very well, which is very good. Although you can drop your lowest test. So, you know, some of you got 8 on this one too, okay? So I can only appreciate, because I have to drop the lowest score, okay? Even some of you get 90, 95, okay? But it's going to be a very good one for your family. If you have any question regarding your test, bring it back at the, at the end of the lecture or during the break. I explain it to you. Okay, that's one. Okay. Now, what we are going to do is we are going to quickly, since we started this matrix form of the solution of a system, you see we did the one that when the eigenvalues are different, distinct. So we need to take care of the case when the eigenvalues are complex numbers and when the eigenvalues are going to be repeated. We do this too, and we hope to give you a kind of a very mild, non-homogeneous one, okay? But a mild one to finish it, okay? Because there are some applications and you may need them in your discipline in future. So let's see how we're going to take care of the case, okay? So we want to solve the system of the linear system, okay? Linear system with the constant coefficient that we did it before. But this case, we are going to have, let's start with the complex, the case 1 that we talked about it before, okay, distinct real eigenvalues. Now we are going to check what would be the form of the solution if the eigenvalues are going to be complex. In application problem, most of the time you are going to get the complex case, okay? So continuing with whatever we did before, this is going to be case 2. Okay, case 2. The second case. This is going to be the case that we have complex eigenvalues. The situation is very much like the one that we did with the linear equations. Okay, complex eigenvalues. So we already tried, okay, the matrix form of the differential equation, and we arrive at the complex. Now, what are we going to do in this case? You see, again, we assume that the A, as usual, is going to be that matrix. Let A be the coefficient. Okay, the coefficient matrix. The coefficient matrix of the system, of the homogeneous system. X prime equal to the AX, the one that we've been working on, okay? So the differential equation are given, we change it into this format. And let K be, okay, let K be the, we find the eigenvalues happen to be a complex number. So for the complex values, for each eigenvalue, you have to find the corresponding K, and then you write the solution. Okay, let K be the corresponding, okay, it's going to be the corresponding corresponding eigenvectors, eigenvector of a complex eigenvalue, of a complex eigenvalue lambda. Now you see, I'd like you to see how we're going to arrive at the formula. There is something that you can memorize it, or you can do it as is. You see, suppose lambda is equal to the alpha plus beta I. So for this lambda, you are going to find the corresponding vector. Your vector is going to be, okay, your vector is going to be in complex form, okay? So the coefficient, if you like, the coordinate are going to be complex, the real number, but the K is in the form of, let's say, in the form of the B1 plus B2I. It's going to be a column matrix. You break it into the real part and imaginary part. So the real part is B1, like the alpha plus beta I. We're going to have something similar for the vector K. Okay, then let's check one of the solution as we did it before. Remember what was the format of the solution? The format of the solution is what? Is equal to the K times e to the, okay, e to the lambda t. Let's check this one in the form of the complex to see what's the result. Substitute. So your K is B1 plus B2I times it by e to the lambda t alpha plus beta I times t. Now let's simplify it. Okay, if you want to simplify it, keep the first one. Like in the linear case, to simplify, you know that this, you can write this one as what? E to the alpha t times e to the I beta t. Then you can change the second one using the Euler formula. Change it into the, okay, trigonometric form. So trigonometric form would be what? Would be cosine of the beta t plus I times sine of the beta t. Okay, I want to create that solution for you. So multiply them together. So this is going to be equal to pull out the e to the alpha t, FOIL the rest. What's going to be the result? When you FOIL the rest, it's going to be B1 cosine of the beta t plus I and B1 sine of the beta t. You multiply this together, is going to be I B2 cosine of the beta t. And the last one would be what? I times I would be I squared, which is a -1. So that gives you minus B2 sine of the beta t. Okay, I just fold them together. So write it down as a complex number. So this is going to be equal to e to the alpha t, the leftover. Put the real part and the complex part together. The real part of what is going to be b1 cosine of the beta t. That's a real part. The other part is this one, minus b2 sine of the beta t. That is going to be your real part. What's going to be the complex part? I times complex part. You get b1 sine of the beta t, okay, plus b2 cosine of the beta t. So that will be the real part and the complex part. Exactly as we did for the, okay, as we did for the case of the, okay, for the case of the linear equations, okay, linear equations, if you consider that, okay, if you consider that real part and imaginary part, that would give you two independent solutions. You see, put them together, this one. So I'm going to call the first one x1. So x1 is equal to what? X1 is equal to the, you multiply them together, it's going to be, that's it, b1 cosine of the beta t minus b2 sine of the beta t times it by e to the alpha t. That's one solution. Take the second one, x2 is equal to, x2 will be what? b1 sine of the beta t plus b2 cosine of the beta t times it by e to the alpha t. You see now I have two solutions. Yes. No, I picked the real part and the complex part. Okay, the real part and the complex part that give me two functions. And these two now is going to be linear independent. Remember, in the case of the linear case, if you have a basis, a linear independent, the linear combination will give you the solution of the equation and be done.
You just drop the I that was very important.
Yeah, you see, it's the real part and imaginary part by itself. Both of them are going to be what? Both of them are going to be solution of your equation, and you can prove that they are going to be independent. Exactly the way you did it for the, okay, for the ordinary linear equation they're going to have. Okay, so x1 and x2 are going to be R2 independent linearly. Independent solutions. Remember, we talk about the Wronskian and not equal to the zero, this type of idea. Okay, solution. Therefore, the general solution of the system is going to be the following. So there you are. X is equal to, again, C1 x1 plus C2 x2 is the general solution of the system. General solution of the system. But you must be careful. Remember that the B1 is the real part of that vector that you create. You can create vector K. B1 is the real part. Okay, B2 is the imaginary part. You put them together. You can do this operation all the time that you solve the equation. Or it would be better, you know, it's easy to memorize it because it's kind of a symmetric. You see, B1 cosine minus B2 sine. This is B1 sine plus B2 cosine. So it's easy to memorize it. And that would give you the solution of the system when you are going to have a complex eigenvalues. Any question? So you saw that equation that we have, characteristic equation. Anytime you see a complex solution, your solution, of course, you know, that's going to be in pair. Alpha plus minus beta I. You don't have to consider both of them. You just take one of them and go back and find the eigenvectors. If you have done, you know, a very mild linear algebra, you know that in this case, when you have a complex eigenvalues, then your vector are going to be also complex. So you have the B1 and B2. Of course, you know, the coefficients are constant. So this procedure can be, you know, can be go through. So this would be the complex case. You should give me an example to see how we're going to apply. Any question? So it would be a straightforward, but as I told you, it's very, very important. In application cases that you have, most of the time, your system would end up with the complex, okay, eigenvalues. So that's why you have to know it to take, you know, to get to it. So example. So that would be case 2. You are going to have 3 cases. Okay, cases. We try to put them together somehow, and we are going to question you again. Okay, for the final. So example, that's it. Solve the system. Solve the system. Solve the system, and this is the system. We have x prime equal to, okay, that's it. X prime equal to the 6, -1. Then you have a 5 and 4 times x. This is the system that we want to solve. Okay, you know what to do. Quickly, we have the matrix, find the characteristic equation, try to find the lambda to see what type of lambda are you going to have, and then take care of it. Are you ready? Solution. Okay, so form the characteristic equation. Determinant of a minus lambda I equal to the 0. So that gives you the determinant of this matrix. Is a 6 minus lambda -1, 5, 4 minus lambda is to be 0. Find the determinant, cross multiply. 6 minus lambda, 4 minus lambda minus. That gives you -5, so that would be a positive 5 equal to the 0. Boil it. So that gives you 24 minus 6 lambda minus 4 lambda plus the lambda squared plus 5 equal to the 0. Okay, so you end up with the lambda squared minus 10 lambda plus 29. 29 equal to the 0. We cannot factor it. Quadratic formula to solve it. So that gives a lambda equal to quadratic formula -10 plus or minus the square root of 10 squared. Okay, 10 squared minus 4ac, 4 times 1 times 29 divided by 2a. Go on. It's going to be a 10 plus or minus inside the radical 100 minus 4 times 29, 160, nice number. So that gives you 10 plus or minus a square root of -16 over 2. Use the complex version. So that gives you 10 plus or minus 4i divided by 2. Break it, simplify it. 10 half plus or minus 4 half times I. So you simplify it, you arrive at 5 plus or minus 2i. So you have a case. You have complex, okay, complex eigenvalues. Any question? So quickly you get alpha and beta. Then you have to find the K, and then you get the B1 and the B2. Then you put them. Yes, that's question.
Do we just use the real part of lambda to solve for the K value?
No, you use the lambda. It's 5 lambda plus 2i. Okay. Just alpha and beta would be the one that you use at the end. Okay. So we use only one of them. You don't need to do both of them as we talk about it. Okay, so we pick the lambda to be 5 plus 2i. You make a note that the alpha is equal to 5. and the beta is equal to 2. So we have to go and find the k. Okay, so we want to find the k. Remember, to find the k, we have to form this equation, a minus lambda I times k equal to the 0. If you go to this format that you have over here and replace the lambda by 5 plus 2i. And then you come back, okay? So this is it. So if you substitute, that's going to be 6 minus lambda. Lambda is 5 plus 2i. Minus 5 minus 2i. Okay? So, and the other one is just a -1. And this is 5. 4 minus lambda, again minus 5 minus 2i. Times it by k. As usual, you call it k1, k2 equal to the 0, 0. Simplify, then multiply. So the top that give you a, okay, that give you 1 minus 2i. That's a -1. The second one would be the same. Doesn't seem to be, but they are. Okay, minus 2i. And this is going to be, you times it by k1 and k2, then equal to the 0, 0. Okay, you multiply them together, but you know that this system is going to be a game dependent system. You just use one of the equation. And this is the first one. I'm going to write it down. So it's going to be 1 minus 2i times it by k1. Okay, minus k2 equal to the 0. This equation would be enough to solve it. Yes.
Why are we only using the positive number, like 5 plus?
It doesn't matter.
It doesn't matter.
Doesn't matter. You need only one of them. Okay, if you remember when I proved it, I just used alpha plus beta for the conjugate. Because when you find the k corresponds to the alpha plus beta I, the other k would be k bar, the conjugate. If you use the conjugate, you get the conjugate of this vector that you're going to find. So that's why we use only one of them. Okay, so that's it. So, you know, you can multiply the second one. You're not going to use it, but I write it down because both cases are going to be the same. Okay, this is a system that we have to solve. Okay, this system is going to be dependent as we did it before. So just pick one of this equation. So pick the easy one. I pick the first one because you are going to have infinitely many solutions. So you need only one of them. Okay, k1 minus k2 equal to the 0. 4 for k2. So the k2 is going to be 1 minus 2i k1. Okay, that gives you infinitely many solution. Just pick one of them. Easy one. What's the easiest solution? You pick k1 equal to 1. You pick the k1 equal to the 1. Then your k2 would be 1 minus 2i. Okay. You can pick, of course, any number you like, but you know that would be easier. Now you form you are going to form your vector. Then you need the real part and the imaginary part of that vector to call it the b1 and the b2. Then bring the formula, substitute, and then you're done. Okay, are you done? I have to go to the next page. So I have the k1 of 1. So I form the k picture. I'm going to record this one. Okay. So that's it. So we continue. Okay, I repeat it again. I'm going to use the k1 equal to 1, k2 equal to the 1 minus 2i. So form the vector k. The vector of k is going to be k1 and the k2. So substitute, that give you 1, and that's going to be 1 minus 2i. It's like the complex numbers. You have to break it to find the real part and the imaginary part. Okay, so you break it into the real part of the first number is 1, the real part of the second one is 1, plus I times imaginary part of the first one is 0, imaginary part of the second one is a -2. You see, this would be b1 plus b2i. So this is b1 plus b2i. imaginary and the real part of the vector k. There you are. So pick the B1. B1 is going to be 1, 1. And you pick the P2. B2 is going to be 0 and -2. Now bring the true solution that we talked about. Any question? So remember the solution that we proved, so we can use it. The first solution was this one, was B1, e to the, sorry, b to the alpha t, cosine of the beta t, minus B2. Okay, B2 alpha t, sine of the beta t. That's the first one. So substitute. You have all the information. Remember the alpha was what? Alpha was, what was alpha? Alpha was 5, and the beta 2. So substitute to get the first solution. X1 equal to the B1, 1, 1, e to the, okay, e to the 5t, cosine of the 2t, minus B2. B2 is 0, -2. Okay, there is an E here that I missed. Okay, this is going to be 0, 2. Again, e to the, okay, e to the 5t, the sine of the 2t. Okay, so that gives you one solution. If you want to put them together, because eventually you have to find that x and the y. So if you want to put them together, so the x1 would be a 2 by 2 matrix. Okay, you can pull out the e to the 5t, so the terms are going to be, you get a cosine of 2t here, 0. So that give you cosine of the 2t. And the bottom one, you get a cosine of the 2t. And over here, negative would be positive. Okay, so we get a plus 2 sine of the 2t times it by e to the 5t. Okay, this would be x1. Any question? Now we repeat it for the x2. The formula for the x2 was just a little bit, just you switch the sine and the cosine. So x2. Okay, x2 is this. See, you start with the b2 now. b2 e to the alpha t, but sine of the bt, beta t, plus b1 e to the alpha t, cosine of the beta t. It's very similar. So you substitute. X2 is equal to, now got the experience, you can write down. B2 is, what is B2? B2 is 0, -2. Okay, so this is going to be the case. Just checking this formula that we did. I think this second one must be, that must be cosine and the sine. Let me just check the one that I proved for you. Let's say this is the one that we proved. X2 is B1 sine of the B2. Yeah, B2 cosine minus, okay, I just switched this one over here. Okay, it's a cosine for both of them. Okay, I think that's the one that we proved. Is the cosine BT minus B2 sine. The second one is sine minus cosine. Sine minus, okay, let's make sure you get it right. Okay, the second one, that's correct. Sine minus, okay. So this is going to be the case. We have the sine of the 2t. Sine of the 2t, then we get the B1, which is going to be 1, 1. Okay, we get the 1, 1 cosine of the 2t. Everything would be e to the 5t. Okay, then you can put them together as a one solution. So x2 is going to be a 2 by 2. For the first part, you are not going to, you are going to get only cosine of the 2t. Yes,
Would it be B1 sine instead of B2 sine?
this one,
Yeah. B1 sine, B2 cosine.
I think you are right. So I just mixed the, what's the formula that I proved? What's the B1? B1. This is B2. I mixed up with my note as well. Okay, so you get the, then yeah, that's the cosine sign. Yeah. So we just switch it. This is going to be 1, 1. Sorry, 1, 1. Okay, so the B1 is 1, 1, and the other one is going to be 0 and -2. That makes sense with the final answer that I have over here. Okay, so that's a 1, 1, and the 0 and -2. So now we get the final answer as I have it in my notes. Okay, so the first part is going to be sine of the 2t, sine of the 2t, and the second part is going to be sine of the 2t minus 2 cosine of the 2t. This is going to be, okay, so the final, this is x1 and x2, of course, x would be c1 x1 plus c2 x2. You can repeat those. Since the system is going to give you in the matrix form, so you give the answer in a, in a metric form, and then you got. Okay, so it's if you have that formula, that's easier for you to do it. Okay, but otherwise, you can try it. At each time. Okay, any question? So that's a complex case. Yes. 1, 1. Yeah, that's a big one. 1, 1. Okay, to get this one, let me just try. I'll give you another one. I'll give you a couple of minutes to try it, to see if you can do it for yourself. Okay, are you ready? So let's see if you can do this one for me. The second example. Try to solve this system. Okay, solve x prime equal to 1, 2, -1/2, 1, x. Give you a couple of minutes to see if you can do this one. From the characteristic equation, try to see what's going to be the lambda looks like. If you have any question, let me know. What you got for the lambda? 1 plus minus I, that's good. So lambda is 1 plus minus I. So you pick lambda to be equal to the 1 plus I. And then you look for the eigenvector. Anybody got the final answer? You got it?
By that one gap.
Okay, let's see the solution. Okay, see what's going to be the case. So there you are. We go with the finding the eigenvalues first. So the determinant of the A minus lambda I is going to be equal to, okay, that's it. 1 minus lambda, 2, -1/2 with 1 minus lambda. We want it to be equal to the 0. So it's 1 minus lambda times 1 minus lambda. Okay. And you multiply this together, that gives a -1, which is going to be a positive 1, equal to the 0. So this is like 1 minus lambda squared. It's going to be 1 minus 2 lambda plus lambda squared plus 1 equal to the 0. Okay, so you end up with lambda squared minus 2 lambda plus 2 equal to the 0. We try this one. So the lambda is going to be equal to -2 plus or minus, okay, 2 squared or -2 squared minus 4ac. So divide by 2 inside the radical. So that gives you 2 plus or minus. We get the 4 minus 8. Again, a nice number. 2 plus or minus radical 4 over 2. -4 into the I. So that gives you 2 plus or minus 2i over 2. You break it, simplify it, 2 over 2 plus or minus 2 over 2i. So the lambda would be 1 plus or minus I. Okay, so we pick 1 plus I for our lambda, and we make a record that the alpha is equal to 1 and the beta is equal to 1. Okay, that's a step 1. Any question? So finding the vector. So finding the vector k, you go to the top over here. Okay, and replace the lambda by 1 plus I. So we are looking for the vector k that satisfy this condition. So that would be matrix 1 minus lambda, 1 minus 1 minus I, 2, -12, 1 minus lambda minus 1 minus I, times k1, k2 equal to the 0. Okay, you simplify the first one that give a -I and 2, the second one 1/2 and -I, times it by k1, k2 equal to the 0. Just one row will be enough. Get this done.
Doctor,
Yes,
you said it doesn't matter if you choose plus I or minus I, right?
here it doesn't matter. Okay, so this is going to be the case. So I'm going to pick the first one. Is a -I times k1 plus 2k2 equal to the 0. Okay. So in this case, you can find the k2 if you like. So 2k2 is equal to the I k1. And then k2 is going to be I over 2 times k1. Okay, I pick a nice number to find it. I pick the k1 to be equal to 2. Then the k2 would be equal to, okay, k2 is equal to the I. So the vector, okay, the vector is going to be 2i. Okay, that's it. The answer would be different when you depend on what type of numbers you pick for the k1 and k2, but the final answer would be the same. Now you break it into the real part and the complex part. The real part of the first one is 2. The real part of the second one is going to be 0. So plus I, the complex part of the first one is 0. The complex part of the second one is 1. So this is going to be your B1 plus I B2. Okay, so the vector B1 is 2, 0. Okay, the vector B2 is going to be 0, 1. Now we're going to form the solution. So we got the formula, substitute to get the x1 and the x2. Okay, any question? So write it down, we'll do done, we put them together. And that would give us the final answer. Okay. So let's go and find the x1 first, x1 and x2. So and that's it, the formula for the x1. The x1, I go with this one, b1 cosine of the beta t, okay, minus b2 sine of the beta t, okay, times it by e to the alpha t. Now you substitute, remember your alpha and beta, alpha is 1, beta is 1. So the x1 is going to be equal to the b1. b1 is 2, 0. 2, 0 cosine of the t minus b2, 0, 1, 0, 1 sine of the t. Okay, sine of the t all times, okay, times e to the t. So put them together to get your x1. Okay, so this is it. The x1 is going to be equal to what? On the first row, we get the 2 cosine t. Here we get the 0. On the second one, we get the 0 here, so it's going to be minus sine t. Okay, it's going to be minus sine t e to the t. So this is going to be your x1. Any question? Now we got the x2. Question?
Oh, yeah, here alpha.
Alpha and beta, both of them are 1 because you get the lambda equal to alpha plus, lambda was 1 plus I. Okay, we go with the x2. So the x2 is going to be b2 cosine of the, okay, beta t plus b1 sine of the beta t times it by e to the alpha t. So you substitute, okay, the b2 is 0, 1. 0, 1 cosine of the t plus b1 is 2, 0 sine of the t. Everything times it by e to the t. So you find the x2. So the x2 is the first component, nothing. Over here you get the 2 sine t. The second component is going to be cosine t e to the t. Okay, there you are. The final answer, C1 x1 plus C2 x2. I'll give you the final answer. Okay, we accept it, but if you want to write it down, it's a C1, that's easy. Again, cosine t, negative sine t, e to the t plus C2, 2 sine t, cosine t, e to the t. Okay, if there was a case to find the x1 and the x2, you know that. Let's find out, in case we ask for the x1 and the x2, not in this case. So x of t is going to be the first one, 2c1 cosine of the t plus, okay, 2c2 sine of the t e to the t. So that's going to be the x, and the y is going to be the second one, minus c1 sine of the t plus cosine of the t e to the t. This would be, if you want to get it as a component. So, it's a nice case that you have doing the application. So I give a short break, we come back. We are going to get the last case, which is it's going to be more involved. What would happen if you have a repeated eigenvalues? We're going to have 2 eigenvalues, but both of them are the same. Okay, you have to take care of the second solution. In the case of the in case of the equation, remember, if one of the solution is e to the lambda t or e to the RT alpha t, the other one would be t e to the t. But you have to modify here because of the vector form. So we prove the second solution and then we do. Okay, so we got 10 minutes, come back and we finish it. Okay. If you haven't got your test back, it's here. That's
So how did you know that when you wanted
doesn't matter. There's a question.
You're already going up in half. I didn't do it, no.
So one of the thank you.
I had a question on, why did I get marked? Was that supposed to like? But I can find, let's see right here.
Yeah, not wrong.
Okay, so I just had to write it all. Yeah. I ran out of time.
Yeah, I know that. Yeah, back in office, there's gonna be a point for the final answer. We went up when
I thought you were much more really beautiful. So.
Yeah.
Sorry, thinking like when you do, is there anything else?
Oh, would be named for it.
Oh, and then,
yeah.
so you say we have one more extra term opportunity for a while?
Yeah.
Yes, you don't have that yet.
No.
Would you go with these?
Everybody, well, everything.
Final term for the extra term for the.
Yeah, there's gonna be.
Yeah. Okay.
You get it, then you get it for. Yeah, that'd be a problem.
I was surprised, I thought different thousand a little bit better, but this one like, I had, what's the thing, since I started out with this one, I was thinking that. That would be as good, and then I pretty much back to like in the same,
Nice one.
No, I haven't. Why did you?
What do you mean?
Like what points were, like which points are less than the exam points?
Everything I have. I didn't get your quiz. Did you select quiz 3?
I did, yeah,
I don't have it.
it's from the DRC. with the-
I have to contact them and send it.
No,
Send it.
not that, it's okay, is the grading scale weighted?
I don't understand what you're talking.
Like if one thing, like are the tests worth more?
You read
Or
your
is it
syllabus, it's, everything is clearly given to you.
I think weighted, but like.
Yeah.
Okay.
Not like.
Okay, you get the, the test, the quiz, that.
Okay,
If you want to get a percentage, you find it.
okay, yeah,
You see? I thought you mean,
no.
you didn't take that one.
No, I did.
But I did
Yeah,
that. Hey, Angela,
what happened? I didn't say something. They had told you. I didn't-
They never. Thanks a lot.
yeah, you just contact them and you did that. I thought you didn't take it. You didn't take it. I check all my emails.
Right, hello.
Yeah, maybe I asked them not to, okay, not to send it, just email. You know, check the message. Maybe they thought, you know. Because they send a hard copy to the, okay, to the center, to the general office.
Right.
You know, in college. That's right. But ask them to, you know. Because they did send.
Yeah. But it was a big goal. I think the problem was and it like it worked out. When you were. Yeah. For sure. I do the same for that. Or you got to go there. No, it's where. When you get it, when they- very, very, like, all of.
Yeah.
I think.
Oh, yeah. That's. That's good.
And you also. Spring break.
Yeah. Yeah. It's like the same thing. Okay.
Yeah, I'll let him check that out.
Oh my goodness.
Okay, let's try to get this last case. Okay, it's very much more involved to get through this one. Okay, case 3. Case 3, when we get the repeated eigenvalues. For the repeated eigenvalues, is like the one that we did in the case of the equations, okay? So one solution, it's fine, it's guaranteed. But you have to look for the second one. You get the second one, it's very similar to what we did before, but you have to do a little bit of modification. So that's going to be case 3. Okay, case 3, that would be repeated eigenvalues. Okay, repeated eigenvalues. Okay, so we have our system again, but we tried eigenvalue thing is going to be repeated. Let's see how we're going to do it. So suppose we have a repeated eigenvalues. Suppose lambda 1 is equal to the lambda 2. We're going to call it lambda because we have only one. Is a repeated eigenvalue. Okay, since it's at least it's eigenvalue, we can find the k for this one. Okay, and k. Okay, and k is the corresponding eigenvectors. It's the corresponding eigenvector. Okay, so we have the first solution. If this is going to be the case, then we have the x1. Remember, x1 is equal to the k e to the lambda t is a solution of a system. Is a solution of the system. Okay, and the system is ax equal to the x prime. But we need the second solution. Okay, so how are we going to find the second solution? Now, how are we going to find the second solution? We are going to propose the second solution as we like it, and then we get the condition that it can be fine if you like. So it's very similar to what we did before. So a second solution, that's a suggestion. A second solution can be fine. To be of this form, of the form, you see the form, x2 is equal to the one that you already got, okay, k times t to the lambda t. Remember, for the linear case, we usually use this one, but this is not going to be enough for this case. And you have to modify it. The modification is this, plus p, okay, p to the lambda t. So k is a vector, p is also another vector. Okay, if you factor out the lambda t, is going to be of this form. Look at this one. It's going to be p plus kt e to the lambda t. This is our suggestion that the second solution is going to be of this form, where or when where the vector p to be determined so that x2 is a solution of the system, is a solution of the system. So we want to force it, if you like. We want to force it, the second solution, to be of this form. So what does it mean? This means, this means x2 prime must be equal to the a times x2. Remember, the solution, x is a solution if we satisfy the equation. So let's form this one. Okay, so we assume that this is the solution. So if it's a solution, it must satisfy. So let's see what is this. Let's find the derivative of x2 prime. This is x2. Differentiate it. What's going to be the derivative? You see the first one, you have to use the product rule. K is a number, of course. Derivative of the first, second first. So it's going to be k e to the lambda t. That's the derivative of the first times second, plus the derivative of the second times first. The derivative of e to the lambda t would be lambda e to the lambda t. So it's going to be plus, lambda is a number. It's going to be lambda k t e to the lambda t. Okay, so the derivative of the first is 1, k e to the lambda t. Derivative of the second one, e to the lambda t, u prime would be lambda. So I bring the lambda here. Lambda k t e to the lambda t. Okay, plus the derivative of this one. P is a constant. The derivative of e to the lambda t would be lambda. So we get the lambda p e to the lambda t. Okay, that would be x2 prime. But you want it to be equal to what? You want it to be equal to the a times x2. So what's going to be a times x2? You see this is the one? Is going to be a times, multiply the a by the x2. So it's going to be what? It's going to be ak t e to the lambda t plus ap e to the lambda t. Okay, it's all algebra. Let's see if you can get anything out of it. Move everything to one side, try to simplify it. Okay. So one thing we can do is e to the lambda t is a non-zero number. So we can drop it. Okay. So we can drop the e to the lambda t. Done. So what's going to be the leftover? The leftover is going to be k plus lambda k. And you get the lambda p. Bring the other one to the other side. Minus akt, and the minus ap equal to the 0. So that would be the conclusion they're going to have. I miss a t. Where I did miss the t? Second one, yes, I need it. Now we do the algebra, factor out that the t. Okay, this is going to be the case. If you factor out the t here, what's going to be the leftover? It's going to be lambda k minus a k. Okay, this is going to be the case. This is going to be k plus lambda k t. Okay, plus lambda p. This is the way I got it over here. Okay. Let me check. That's a k. It's a lambda kt. Lambda kt. Huh? No. the one that I put over here. I factor it out here. Yeah, that's you are right. So it's going to be lambda minus AK. Very good. Okay, so what's going to be the leftover? The leftover is going to be, I just want to factor these. Okay, let's write it down. So it's going to be lambda P minus AP plus K equal to the 0. Let's do a little bit more. So we have the T over here. You see, you cannot write lambda because this is a vector. So you have to write lambda I here. Yes.
What about the K?
Which K?
Next to the, we factor out and B, is one thing, K, I.
Factor out the T here, so that give you lambda
K, I.
lambda K. Okay, okay, lambda K I. Sorry. I just looking for the. Okay, so I'm going to write it down here for you. You see, I pull out the K here. So there is a K here, factor it out. Okay, that's what I was looking for, in fact. Okay, next, I'm going to take care of this. I factor out the P. So if I factor out the P, what's going to be the result? Lambda I minus A. Remember, because they are vector matrix, you have to write lambda I. So that gives you P. Okay, P plus K equal to the 0. Okay, so that's what you get over here. So this is going to be an equation. The only variable that you have, a scalar, is T. So this means in order that x2 to be solution of your equation, this identity must be true for all values of x, for all values of t. It's like an identity. It's like a polynomial. Remember, if this is going to be true for all values of the t, this means, you know, this is a linear polynomial in t, and on the other side is 0. So they are going to be equal to each other if the coefficient of the monomials are going to be equal to each other over there. So on the other side, you have only 0. So what are you going to do? The coefficient of the t must be 0, which is lambda I minus A times K must be equal to the 0. This is one of them. And the leftover is going to be considered to be constant. So the leftover is going to be lambda I minus A times P plus K equal to the 0. Okay, everyone understand? It's a linear polynomial to the left. Linear polynomial is like what? It's like mx plus b, if you like. So the coefficient of the t here is a lambda I minus A times K. The constant term is this one. But on the other side, you get 0 only, okay? Look at this one. You can write the other side as 0t plus 0. So you let the coefficient to be equal to each other. That gives you two conditions that you have to follow in order to be able to find the second solution. I'm going to write it down in a standard form. I multiply this one by -1. So I get A minus lambda I, as we did it before. A minus lambda I is going to be times K must be equal to the 0. That's the first one.
But it is negative then?
No, both of them are, you see, on the other side is 0. So I just multiply by -1. A minus 1.
Negative factor, you won't.
That's it. And the second part, I do the same thing to the second part. So it's going to be the second part. A minus lambda I times P minus K equal to the 0. Now, once more, what is going to be the conditions? A minus lambda I times K must be 0. That's the first condition. The second condition, A minus lambda I times P must be equal to the K. You see? Look at these two conditions that we have. So in order that second part that we suggest, x2, to be the second solution, these two conditions were satisfied. The first condition is not new because you use this one to find the x1. But the second condition enable you to find the p. You find the p, you go back, and you have the second solution that you are going to be interested in. Okay, so this would give you, you see, this would give you the first solution, which is x1 equal to the k e to the lambda t. That would give you the second solution. The second solution, which is going to be p plus lambda t e to the lambda t. That give you, again, both solutions going to be linear independent. Okay, x1 and the x2 is going to be linear independent. So x1 and x2, x1 and x2 are two linearly independent solutions. So you have the general solution. X equal to the C1 x1 plus C2 x2. And you're done. It's very easy to find because you already know how to form this one to get the K1 and the K2. You are going to form the second one, you call this one P1 and P2. And you put them together, both systems are dependent system. You are going to have infinitely many solutions. So quickly you can find one of them, put them together, and that give you the final answer. Okay, so I just wanted to prove it so that you can see it really to get these numbers. Okay, any question? So let's do it. A system would be given, you are going to have a repeated solution, lambda. You do as you did before to find the k that give you your first solution, then you come back, you repeat it again. This time using this equation, a minus lambda I times p equal to the k. And then that gives you a second solution to put them together, and then you're done. Okay, any question? Let's see what will happen when you want to do it. There you are. Solve this system. They give you one from each on the final. Okay, there are three cases, three problems. It's straightforward. Okay, and there is going to be a fourth one. We want to give you a very mild, non-homogeneous one, very mild one. Okay, it takes time if it's going to be a little bit more involved. Okay, need a little bit of linear algebra. Okay, there you are. Solve this system. Solve the system. What's the system? X prime equal to 3 and negative 18, 2 and negative 9. X. Okay. So start the procedure. Get the lambda first. Solution. As usual, determinant of a minus lambda I equal to the determinant would be 3 minus lambda, negative 18, 2, negative 9 minus lambda, equal to the 0. Cross multiply to get determinant. 3 minus lambda times negative 9 minus lambda. That would be 36 negative, but you have a sign here, positive 36 equal to the 0. Okay, FOIL it. Negative 27. Okay, negative 27 and negative 3 lambda, and that's going to be plus 9 lambda plus lambda squared plus 36 equal to the 0. Combine the like terms. Lambda squared minus 6 lambda. 6 lambda, you have 27 and 36, that give you a positive 9. It's a perfect square. Lambda minus 3, all square equal to the 0. So we get the repeated solution.
Isn't it plus 9 minus 3, so it's not plus 6?
You are right, plus, very good, plus. So we get lambda equal to the negative 3 is going to be a repeated, okay? It is a repeated solution. is a repeated, okay, repeated solution. Okay, we continue as usual to get the first solution. Okay, so we go with the lambda equal to the -3. We are going to form this vector. Remember, a minus lambda I times k equal to the 0. So you put the lambda here, and you multiply by k. So the lambda is a -3. So we are going to get a 3 minus -3 would be a +3. -18 to -9, -9 plus. Okay, it's going to be -9 plus 3 times it by k1, k2 equal to the 0. So that gives you 6, -18, and that would be 2, -6. All of them are the same. K1, K2 equal to the 0. Get one of them, you multiply the second one by 3, you get the first one. So form this 6 K1 minus 18 K2 equal to the 0. Okay, divide by 6. K1 minus 3 K2 equal to the 0. So we get the K1 is equal to the 3 K2. So pick a number for K2 and get one solution. So the easy one, K2 equal to 1, and the K1 equal to 3. So the vector K is going to be, okay, 3, 1. That is the first part. That gives you the first solution, you know that. So that gives you your first solution, which is going to be your x1, which is k e to the, okay, lambda t is going to be 3, 1. E to the lambda is equal to -3. -3, okay, -3t. So this is the first solution. We put them together. Now we have to find the k x2. Remember the x2 for the repeated one. For the repeated one, the x2 is equal to. Okay, the x2 as we proved it is going to be equal to the p plus kt e to the lambda t. Now we're going to find the p. P would satisfy this condition. A minus lambda I times p equal to the k. So go back again to the matrix that you did have. You already simplified that. See this one? This is the matrix, 6 minus 18 to -6. And you multiply by p, you already equal to the k. Okay, so that's it. 6, -18 to -6. This time multiply by p. You call it p1, p2 is missing, equal to the k, which is 3, 1. This is the way you're going to find the p. Okay, any question? Because you already done the part a minus lambda I, so you have it. So multiply it, and then again, you can use only one row. So if you're multiplying together, this is going to be the result. So that gives you 6 P1 minus 18 P2. That would be enough, but I do the second part too. 2 P1 minus 6 P2. Give you 3 and 1. One row would be enough. These are two vectors, and they are going to be equal to each other if they have the same component. So pick one of them. It doesn't matter. I pick the first one. 6P1 minus 18P2 equal to 3. You divide by 3, you get exactly the second one. Okay. You divide it by 3 or divided by 6, divided by to get the P1. So that gives you P1 minus 3P2 equal to the 3, 6, which is 1/2. Okay. So there you are. So you have a relationship between these two, and you just pick one number. P1 minus 3P2 equal to the 1/2. Okay, any question? Go to the second page to next page to finish it. Okay, you can pick any number you like for this P1 and the P2. So I repeat this one again. So I have it P1 minus 3P2. The way I did it, it's a 1/2. Okay, any number would be fine. What's the easiest number? 0. P2 0. Okay. If you put P2 0, so P1 would be half. So the vector P is going to be 1/2 and 0. That's it. Remember, you already got the vector K. Okay, what is the K? K is 3, 1. So we are ready to get the X2. Okay, we got the X2. Okay, remember the X2 is P plus KT e to the lambda t. You substitute. So P is 1/2 and 0. Okay, plus K is 3, 1. Okay, 3, 1 times T, and then e to the, okay, e to the negative 3T. So that would be your X2. And you put them together, you have the final. Okay, so there you are. In this case, so the X, if you like, X is equal to the C1, X1 plus C2, X2. It's going to be, in this format that we have, we are done. You can rewrite it if you like. So that give you C1, X1. Okay, X1 was the K, 3, 1. Okay, e to the negative 3T. And we get the C2, just repeat this one. 1/2, 0, 3, 1, T, everything e to the negative 3T. So that give you the final number. Even if you can find the X and the Y, or the first component and the second component. And you get this one and we're done. Okay, so it's very nice, nice procedure to get this through. Okay, any questions? Right, done? Yeah. Yeah, that's it. Yeah, separate. I should give you one more. All these problems can come with the initial value. So sometimes they may give you initial value. In that case, you have to find the C1 and the C2 at the end. Okay, so let's try one of them to finish all the possibilities. Okay, I'll try one with the repeated one. Let's just want to make sure we get this one. Okay, then we're done. As you can see, it's a nice system. It can be extended. This is a system of two. It's like a system of two equations, two variables. We can extend everything. We get this true. Okay, let's check this last example, because when you get your review for the final, you will see a couple of these cases as well. Just a reminder. So solve the system. Okay, solve the system, and this is the system. X prime is equal to 2, 4, negative 1, 6, and then initial value. With the initial value of X of 0 is equal to the negative 1 and 6. You see, if they give you in this form, this means you have to do an addition.
Multiplied by X.
Oh, that's X, yes. That's the X. That's the X, okay. Just make sure it's different from what I did. Yes, it's different.
So we do the whole thing the same way. It's
Yeah, you do the whole thing at the end, but at the end, you have to apply this condition to get the C1 and the C2.
Okay.
Because you have the initial condition. Okay, so let's try to find it first. Okay, this is it. Start with the matrix solution. So we are going to find the determinant of the A minus lambda I. Okay, which is equal to the determinant of 2 minus lambda 4, -1, 6 minus lambda equal to the 0. Cross multiply to get determinant. 2 minus lambda times it by 6 minus lambda minus, that give me -4, make it the +4. Boil it. So 2 times 6 to 12 minus 2 lambda minus 6 plus lambda squared plus 4 equal to 0. Carefully simplifying. So that would be lambda squared minus 4 lambda and 16, which is nice. We get the repeated solution.
2 minus lambda.
Is it? -8, yes, you are right. I got the 16 and I didn't care about the rest. Okay, so it's going to be lambda minus -4 whole square. Okay, so we get the repeated solution. So lambda equal to 4 is a repeated solution. Repeated solution. Start working on the first one. Okay, for the first solution. So we need to form A minus, okay, A minus lambda I times K equal to the 0. You have to work on this one. A minus lambda I, this is it. You substitute for the lambda equal to 4. So that would be 2, use this version. 2 minus 4, 4, -1, 6 minus 4 times K, K1, K2, 0. Simplify that, giving -2, 4, -1, 2. As you can see, all the rows are the same. Let's use one of them. -2K1 plus 4K2 equal to the 0. We can divide by -2 and then we'll continue. So that give you K1 minus 2K2 equal to the 0. So you have a relationship K1 equal to the 2K2. So you fix the K2 equal to 1. And the K1 would be equal to 2. Okay, so your vector is going to be 2, 1. Okay, this is going to be a vector, and you arrive at your first solution. X1 is going to be 2, 1, e to the lambda t, 40. That is the first solution. Okay. Now you have to work on the second one. Work on the vector P. You get the second one. Any question? Are you done with this one? Okay, so let's go and form for the second one. So we need to find the x2. Okay, we know that the x2 is going to be equal to, okay, x2 is equal to the p plus kt e to the lambda t. So we have to find the p must satisfy this condition, a minus lambda I times p equal to the k. We'll go back to the matrix that you simplified already, and you bring it here again. Remember, this is going to be the simplified form. -2, 4, -1, 2. -2, 4, -2, 4, negative 1, 2. That will be times that by the P1, P2, and equal to the matrix, equal to the K. Okay, and the K is 2, 1. Okay, quickly, that would give you the P. Just one row is enough. Negative 2P1 plus 4P2, the first row is equal to 2. And we divide by negative 2. So that gives you P1 minus 2P2 equal to the negative 1. Okay, then you pick a number for the P2. Okay, P2 equal to the 0, or P1, doesn't matter, or 1. So the P is a negative 1 and 0. You know that there are infinitely many solutions. So that would be P. So we are ready to give you the second solution. So the x2 is equal to the P negative 1, 0 plus TK. Okay, TK 2, 1 times it by e to the lambda t, e to the 40. So that's going to be your x2. Put them together to get the solution, generate that solution, and then work on the initial conditions. Okay, so there you are. The final answer is x equal to the C1 x1 plus C2 x2. So this is going to be x equal to C1 x1. Okay, x1 was 2, 1 e to the 4t plus C2. C2 times this negative 1, 0. Okay, plus t times 2, 1. Everything e to the 40. Okay, that's the one. Now we can write down in the matrix form, use the initial condition that you have. Okay, your initial condition is that x of 0, if you like. This is x of t, remember. This is x of t, so you have the x of 0 is equal to negative 1 and 6. So put the t equal to the 0 and let this to be equal to the 1 and 6. So if you put the 0, that gives you C1, 2, 1, e to the 0, plus C2, C2 times negative 1, 0, t is 0. So that gives you 0, and e to the 0, equal to the negative 1 and 6. Any question? I just put t equal to the 0 and let the function to be equal to the negative 1 and 6. Now, simplified, e to the 0 is 1. Okay, so first component, you see, this is going to be a 2C1. 2C1 minus C2 is going to be the first component of this matrix. Okay, and the second components are C1. That's it, C1 plus 0. Okay, C1 plus 0. C2, I didn't miss anything. T was equal to the 0. Okay. So that's it. Okay. So this is going to be equal to the condition that we have, negative 1 and 6.
Oh, wait.
No, I put the t equal to the 0, so that give me 1. So over here, t equal to 0, we lost this one.
Oh, yeah.
It's a negative 1 and 0. So the second component, we get only C1 here. Okay, there you are. So it's going to be 2C1 minus C2 equal to the negative 1, and the C1 equal to the 6. So substitute in the first one is going to be 2 times 6 minus C2 equal to the negative 1. So it's a 12 minus C2 equal to the negative 1. Negative C2 equal to the negative 13. So the C2 would be 13. So you go back and rewrite it. X is equal to the C1, which is 6 times 2, 1 e to the 40 plus C2, 13 13 times -10 plus t 21 e to the 40. So that gives you particular solution for that initial case that we have. Okay, so that's it. This is how we solve the homogeneous system. When it's going to be non-homogeneous, it depends. It takes quite a while to do it if it's going to be non-homogeneous, because you know that it's like the one that we did before. If you want to solve a non-homogeneous system, you have to solve the homogeneous one first. Then you have to find a particular solution. In order to find a particular solution, you have two choices: variation of parameter, or what is the other one? Method of undetermining the coefficients. Okay, even if you want to have a very mild one, like a linear one, okay, it takes time. It's not bad, but we usually go with something with a constant, just to try it, to remind you that you know how we're going to do this one. Variation of the parameter is a very good one, but if you want to understand it completely, you need a little bit of linear algebra, because there's going to be an inverse of a matrix involved. And there is a formula, you can memorize it. But if you want to prove it, you need that part. But I will be happy only with the undetermined coefficient, just easy case. In case in future you see it, then you know how to handle it. Because you don't know in application problems, then you can know, where to look for it. Okay, just very mild one. And then we finish it. So I post your final review, okay, over the weekend. So you get the idea, and then we move on next week. We finish this non-homogeneous one, and then we start working on the final review. So the final would cover anything you did on test 3. On test 3, just a kind of 2 or 3 questions from the past, which is going to be solving a non-linear differential equation. Remember, the one that you reduce the order that give you a differential equation of the first type, separable variable, etc. This is how we check, how we cover the first part. And then we give you one Euler-Cauchy equation to solve. It's not going to be homogeneous, so you have to use variation of parameters. So in this case, we cover everything on the final, except series. Don't mind about the series. That's it. Yes. Yes. Final review. Yeah. I have to put them together. I'm very busy.
I'm
But
sure.
I'm busy, Let's wait over the weekend. We have enough time over the weekend, and then next week practice, and then the final. Okay. Good luck. Okay.